Hello, calculus students. So we are going to finish these notes for the straight line motion revisited. In class, we talked about how if you are given the acceleration, you can find the velocity by taking the integral of the acceleration and then adding whatever constant you get from the initial value that it gives you. So it gives you a point, it gives you the acceleration, and from that you can take the integral to work backwards and find the velocity. Next, we're going to think about what happens when you take the integral of the velocity. And there are two things that you can find. And so we're going to start by defining two terms. Displacement and distance. You maybe have talked about displacement and distance in physics. We also talked about it first semester. But let's start with a scenario. So I like to hike, right? I've talked about hiking a little bit in class. So let's say I hike 80 miles to the right. I'm in super good shape. And then I turn and I walk 60 miles back to the left in that other direction. Okay, so I went 80 miles right, then turned around, got 60 miles right. Then I realized that was too far, and I guess I just passed out there. I passed out, I'm done. My displacement is 20 miles, because that is how far I am from where I started. Basically, it's like, oh, you only moved 20 miles. The distance is how far I walked. So my total distance I walked was actually 80 plus 60 was 140 miles, but I only ended up 20 miles from my starting place. Okay? So displacement can equal distance if you walk in a straight line and never turn back. Okay? So these will be equal to each other when a particle, we'll say particle moves constantly in the same direction. So for instance, if I had started, walked 80 miles, and then camped and stayed there, and I didn't turn around, my displacement would be 80 miles because I'm 80 miles from where I started, and the distance that I traveled is also 80 miles. So the displacement and the distance are equal to each other in that case. But we want to see what that looks like in terms of math, in terms of a math equation. So go ahead and pause me and read this paragraph. Read this paragraph, pause me. Okay. And so what this is going to look like mathematically is my displacement is the integral of the velocity, and the distance is the absolute value of the integral of the velocity. Okay? So the reason why displacement is just the velocity is because remember that integrals can have positive and negative area. So the integral takes into account when are you moving right and when are you moving left, and it will subtract the distance when you move left automatically. But if we want to find the distance, we don't want to subtract the times we're moving left. We want to add the times we're moving left, like we did here. We added 60 even though we were moving left. So you take the absolute value to make everything inside the integral positive, so you end up adding everything. Okay, let's look at this in example 3. Okay. Particle is moving along a straight line with this velocity in feet per second. Find the displacement and distance traveled on the time interval between 1 and 7. So displacement is the easier value to find. The displacement you just find from 1 to 7, t squared minus 7t plus 10 dt, because this is my velocity function, the integral of the velocity function. Okay, you should all know how to do this. You can pause me or erase me, try to beat me to the final answer as I do this. 1 to 7. Plug in. 7 cubed is 343. Okay. This is something that could actually be on your AP exam, the non-calculator section. Oopsies, my phone. So the way that I handle these is to kind of combine these fractions together now. So I would subtract 1/3. This is 342. These fractions are maybe a little big for a non-calculator section, but I wouldn't put it past them. Okay. In sum, this ends up being 6. The displacement was 6. So we don't really know what was happening with this function. It was probably moving left and right and left and right. And then in the end, it ends up moving a total of 6 spaces. Okay, that's displacement. Distance is a little bit more challenging. So distance, I'm still going from 1 to 7, but I would need to take the absolute value of t squared minus 7t plus 10 dt. Okay. If you do not have a calculator, there's an algebraic technique that you can use to solve absolute values. Basically, you need to break up the function into the parts for which it's positive and the parts for which it's negative. So I'll show you what that means. Here's the graph of x squared minus 7x plus 10. So this graph is positive from 1 to 2, then it's negative from 2 to 5, and then positive to 5 to 7. I'm going to change this to the absolute value graph real quick so you can see what that looks like. And the way I like to get absolute value is I just type in abs and then you put parentheses around it. So abs is an easy way to get the absolute value bars. And you can see it changed it to absolute value bars. Okay. But let's look at this graph. So when I took the absolute value of this graph, what it did is it took all the parts that were below the x-axis and it flipped it up. So it reflected it up. So algebraically, the way to reflect a part of the graph is to put a negative sign in front of it. So the integral between 2 and 5 needs to have a negative sign in front of it. So what this is going to look like is this. I'd have to split this up into 3 integrals. One going from 1 to 2, and it would just be a v of t. Well, I'll write what it is. So v of t is t squared minus 7t plus 10 dt. And then the next one, I'm going to subtract between 2 and 5. And I'm subtracting between 2 and 5 so I can flip this part of the graph up. And I'll just write v of t now to save time. And then this one, you would add between 5 and 7 of v of t dt. Okay? The other way, if you don't have, obviously if you don't have a graph, it's hard to know what those, well, it's not hard to know what those points are. You have to find them algebraically. So you would take this, set it equal to 0, and factor. And you get t minus 5 times t minus 2. So t equals 2 and t equals 5. And so these are basically these points from which it changes from positive to negative. So these are the zeros where it changes from positive to negative, and you would have to figure out, okay, on which sides of 2 and 5 is this positive and negative, and we just saw that it's positive, negative, positive. So that's the way to do that algebraically if you don't know what the graph looks like. Okay, this is a lot, because basically for each of these integrals you have to do this process. Ugh, too much algebra. I think this is more algebra than it would make you do on the actual AP exam. I'm going to show you how to do this on your calculator, actually. Switch over. So my favorite way to type an integral is to press this button here. It's like, so you see where that red button is lit up. That is a template, so it's a template for basically anything that you will need to do. You see on the top there's templates for fractions and powers and square roots and logs. And then there's derivatives, and on the bottom row there's limits. Ooh, limits. And there's also integrals. So I'm going to choose this integral template. And I'm going from 1 to 7. And again, I'm just going to type in abs, the absolute value with parentheses, x squared. I'm changing it from t to x just because that's, I don't know, it's easier to type in. Minus 7x plus 10, and then I just say dx, 15. So this, if we were to do all that algebra, would equal 15. Okay. So most of what I just said is summarized in these pictures. So if you need to take some time to read this, that is totally fine. The only thing that I'm going to say is these calculator, this is how to do it on your TI-84, and if you want to practice, you can totally practice. So on your TI-84, to get to the integral, which is this FNIT, you hit the math button, and it's math, so math button, and then you hit 9, which says F function integral, is what that means. So you can practice this on your TI-84. I think it's a lot easier on the Inspire, so you can come in and also practice on your Inspire in class tomorrow. Example 4, I want you to practice on your own. So pause me and try to do that one on your own. Hit pause and do that on your own. Okay, and then in the end, you can check your work right here. This is what you should get. So velocity is the integral of the acceleration plus c. Note that I did not, at first I made the mistake and included them, but you do not want to include your bounds because we're looking for a v of t. We're looking for an equation of the velocity. And so I do not want to plug in 0 to 16 on my integral because that would give me the value at 16. I'm just looking for the general v of t. So take the antiderivative and use the point that it gives me, so 0, negative 18 to get this velocity equation. And then displacement, I go from 0 to 16 of my velocity. Distance, 0 to 16 of the absolute value of the velocity. Okay. Use a calculator on this. I do not think that you would have to do this type of algebra without a calculator. We're going to skip example 5 for right now because it's a little tedious to do for notes. Go ahead and flip to example 6. I'm going to make an amendment for example 6. We're going to say let ds dt equal 1/2 t squared minus 3t, and we're going to say on the interval between 0 and 10. Okay. So ds dt is the derivative of the position function. The derivative of the position function is velocity. So I'll just make a little note that this is the velocity.
A asks you to describe the particle's motion.
I remember we did this first semester and people really struggled with this, so I wanted to review what this means. So the particle's motion is talking about whether it's speeding up versus slowing down. And in order to determine whether it's speeding up or slowing down, you compare v of t and a of t. So we're going to make charts for v of t and a of t and compare them. When they are the same, so if v of t and a of t are both positive or both negative, the particle is speeding up. If v of t and a of t have different signs, one positive and one negative, the particle is slowing down. Okay. So to make a chart, we take our function. So v of t equals 1/2 t squared minus 3t, and we set it equal to 0 and find the zeros. So I'm going to start by factoring out a t. And here I'll get t equals 0. Here is 1/2 t minus 3 equals 0. So t equals 6. Okay, I'm not going to make my chart of this quite yet. First I'll find a of t. So a of t equals t, so taking the derivative of this, is t minus 3, set it equal to 0, and I get t equals 3. So basically for the velocity, I found my critical values, and for acceleration, this is a possible point of inflection, because this is the second derivative, so it's a possible point of inflection. Let's make little charts. So here's a chart for v of t, and they both start at 0, and then here's a of t. This will also start at 0. And then I just have 3 down here and 6 over here. So, in v of t, if I plug in 2, I would get 2 minus 6, that's a negative number. And if I plug in 10, I would get 100 divided by 2, so 50 minus 30, that's a positive number. So velocity goes from negative to positive, so this 6 is a minimum. That makes sense, because I just have a parabola that has not been reflected, so it's just a parabola. So 6 is a minimum. And then for the acceleration, let's say I plug in 1. 1 minus 3 is negative. And then if I plug in 10, I get a positive. So 3 is a point of inflection. There is, it changes concavity from concave down to concave up at that point. So I'm going to highlight everywhere where the signs are the same. So both the signs are negative up until 3. So because they're both negative, they're speeding up at that point, those points, the interval. And then from 6 to 10, because this thing, I guess it ends at 10, according to this problem. So from 6 to 10, it is also speeding up because they're both positive. This space in between, velocity is negative, acceleration is positive, so the particle is slowing down. So if I were to describe this motion, I could just write a little summary statement. I'll write my summary statement in this box. Ooh, summary statement. The particle is speeding up for t on the interval from 0 to 3 in union with 6 to 10. So from 0 to 3 and 6 to 10, it's speeding up. And I'll write this explanation because v of t and a of t have the same sign. Okay. And you could write a similar sentence explaining that it is slowing down from 3 to 6 because v of t and a of t have different signs. That's describing the particle's motion. This is review from first semester. Everything else is pretty new. Okay. So the displacement is just the integral from a to b of v of t. So in this case, it is the integral from 0 to 10 of 1/2 t squared minus 3t dt. Go ahead, pause me and try to solve this. Okay, so you should have gotten this right here. C is a great problem, and it is a new idea. So if s of 0 equals 5, so this is giving us what is called the initial position. It's telling us the position, the starting value, or the initial value at 0. So the initial position, or initial value, is equal to 5. And it's asking, what is the particle's final position? So the little equation you can think about here is that the final position is going to equal the starting position. So wherever you started at, plus the displacement. Okay, so wherever you start, plus wherever you displace, however far the displacement is the distance from the starting position, that's your final position. That makes sense. So here, my starting position, we were told, was 5, and then in the previous problem, we found the displacement was 100 over 6. If I didn't have a calculator, I would get a common denominator of 6 by saying this is 30 over 6 plus 100 over 6 is 130 over 6. This is a very important concept. Your final position is wherever you start plus your displacement. Okay. Find the total distance traveled. So total distance traveled is the integral from a to b of the absolute value of v of t dt. So if we had to do this by hand, I want you to consider like how I would split up the integrals. So looking at my v of t, I see that my v of t is negative from 0 to 6. So in order to take the absolute value of it and make it positive, I would take the negative integral from 0 to 6 of v of t dt plus, since it's positive from 6 to 10, I can just leave 6 to 10 normal, v of t dt, like that. Okay. Go ahead and solve this out. I'm gonna flip over to my calculator and do it over there just to get you another look of that. So going from 0 to 10, I'll write abs. If you want to do this on the absolute value on your TI-84, or yeah, I'll show you on the TI-84 actually, since that's what you're using right now. So this will be the integral, so I'll hit math 9 from 0 to 10 Fortunately here you can't just type abs like I like to do, so you have to go hit math button, and then number, so go over to number, and the first thing on the list is the absolute value. So this is the absolute value of 1/2, I'll say 0.5 x squared minus 3x dx. It's thinking 52 2/3. Or if you prefer decimals, 52.667. Okay, we have one more problem. This is a fun one, I think, but you know I'm weird. Okay, so flip the page. Ooh, it's a graphical interpretation of distance and displacement. Okay, so the graph below shows the velocity of a particle. The particle's initial position is x of 0 equals 12. So position can also be in terms of x. Here's my initial position. So that might come in handy later. So you just see this little graph. These numbers represent the area under the curve. So you can think this is the integral. Basically, that's the integral from 0 to a of v of t dt. This is the integral from a to b of v of t dt. Okay? These represent area. What is the particle's displacement between 0 and c? So displacement between 0 and c is v of t dt. So it's just all these areas added together. Remember that since this is negative, displacement takes into negative signs into consideration. So this is 5 minus 10 plus 2 is equal to -3. So from where it started, its ending position is actually 3 spaces or 3 units behind. It moved back 3 units. But it was just because it moved back 3 units doesn't mean it wasn't moving a lot in between. So we can calculate the total distance. This would be from 0 to c, the absolute value of v of t dt. And so just like we broke them up before, we can break them up now. So we can go from 0 to a of v of t dt. Since 10 is the negative one, since that one's negative, we want to make it positive, so we'd say minus the integral from a to b of v of t dt, and then this would be plus the integral from b to c of v of t dt. This integral is equal to 5 minus -10 plus 2, which is 5 plus 10 is 15 plus 2 is 17. So overall, this particle moved a lot. It did a lot of movement. 17 units. And now we want to figure out the position at each of these points. So remember, when we're finding what the position is, we have to consider the initial position. So the initial position is this x of 0 equals 12. This is where it starts. Then at point A, we have to take into consideration where it started from, and then however much we're adding. Like that. And then for B, basically, since we know at A it's at position 17, then we can go from there. We can say 17, at A it started at 17, and then we subtract the 10 to get to 7. And then at x of c, so its final position went from 7 plus 2 equals 9. Okay, so if you need to take a moment to pause and figure out where all these numbers come from, you can do that. I do want to point out that if you look to see where it started to where it's ended, this was indeed displaced by -3 units, which is what we came up with in part A. So it did go back 3 units, from 12 to 9. Okay. And then the last problem, D, when does the particle achieve greatest positive acceleration and then negative acceleration? So here, basically what we're doing is we're maximizing and minimizing the acceleration. Okay, and just like we talked about in class, whenever you're maximizing and minimizing something, you consider the derivative of that thing. So since we're maximizing acceleration, you take the derivative and set it equal to 0. So you consider all of the points where it's equal to 0. So A prime is equal to 0 whenever v of t equals 0, which if you look at the graphs is at points A and B. And then you also have to consider, so these are my critical values, and then also consider the endpoints t equals 0 and c. So in this case, it's kind of annoying. We are considering every single point. So these two zeros, and then endpoints A and C. Okay. We already did find all these values, so it is easy to see that our maximum is here at A and our minimum is here at B. So there's a maximum of 17 at t equals A. And I do want to note this is, you can also say this is the maximum because v of t changes from maximums change from positive to negative at t equals A. Okay. So it's a maximum not only because this problem tells us that, we already found all the values, but it's also a maximum if you think this derivative, v, changes from positive to negative, and so, yeah, there's going to be a maximum at A. We would just also have to compare it to the endpoints to know if it's the greatest maximum or the absolute maximum. And then B is definitely going to be a minimum because it changes from negative to positive. So we would say, and I'm going to write absolute, so the absolute minimum of 7 at t equals B. And you could follow up with v of t changes from this case negative to positive at t equals B. Cool problem. Alright, we'll do some more practice problems tomorrow in class. I'll see you then.